Welcome to the course on error control coding and introduction to convolutional code. So, before we go to concatenated codes, let us spend some time solving some problems. So, the first question is, you are given a rate 1/3 convolutional code with generator matrix G of D, which is given by this. The first question is this a catastrophic encoder? Will an encoder which has a generator matrix like this, will this result in a catastrophic encoder? So, if you recall, what is a catastrophic encoder? A catastrophic encoder generates a finite weight output corresponding to an infinite weight input sequence. Now, if we try to look it in terms of state diagram, in a state away from all zero state, there is a self loop around a state where a non-zero input results in all zero output, right. Now, let us look at this generator matrix and let us try to simplify, put it in a minimal form. So, we can see the denominator, this 1 plus t square is common. So, if we take that out, we get here 1 plus d square, and this is 1 plus d square. This is 1 plus d square plus d4 divided by 1 plus d square, and this is 1 plus d square. Similarly, we see in the numerator there is a common term 1 plus d square. If we take that out, what we get here is then this is 1 plus d square and 1 plus d square. Now, how do we know whether this will result in a catastrophic encoder or not? So, look at this particular generator matrix. Now, what is my output sequence? My output sequence Vd is Ud times Gd. Now, is there any input sequence which is of infinite weight, but can result in a finite output weight for Vd? Now, if we pay close attention to G of D, we notice that if our input U of D is chosen as 1 plus d4, 1 plus d square, if our input is chosen in this particular fashion, then what will be the corresponding output Vd? If the input is chosen this way, then output will be Ud times Gd. So, this term will cancel these terms. So, what you will be left with is this. So, your V of D would be 1 plus d square and 1 plus d square. And what is the weight of this? Delete kar diya wo ganda. So, note here, so the input that will cause this output is given by 1 plus d4 by 1 plus d square, right. Now, we can expand this. So, let us say 1 plus d4, this is 1 plus d square. So, let us just take 1 plus d square, this will be d square plus d4. Now, this will be plus d. So, this will be d plus d square plus d cube, and then this will be d cube plus d4, we can write d square. So, like that basically we can see that this is a infinite series. The input is an infinite series, 1 plus d square is essentially an infinite series. We can expand it like that, whereas output is a finite series. It is just 1 plus d square, and the third bit is 1 plus d square. So, you can see input has lots of ones in it, but the output has finite ones. So, this is a case of catastrophic encoder. Now, the second question is, what would be the minimal encoding matrix for the generator matrix given in the previous example. So, if I ask you find out the minimal encoding matrix for this encoder. So, what do? We take out all the common factors. So, if we take out common factors, then we basically what we get is like this is our minimal encoding matrix, and if we can write, if I ask you to draw this encoder, we can, this is k is 1, n is 3, the maximum memory is 2. So, I am drawing 2 memory elements here. The first coded bit is just 1. So, this is the information sequence that goes in. Second one is 1 plus d plus d square. So, that is your, let us call it V0, this is V1, this is U0, and the third bit coded bit is 1 and d square, this is your V2. Okay. So, this is the minimal encoder for the same generator matrix given in the previous example. So, consider a rate 2/3 non-systematic feed forward encoder. So, this is a generator matrix for a non-systematic code, rate 2/3, and it is a feed forward encoder. There are no feedback polynomials here. The first question is, draw the controller canonical form realization for this generator matrix. Now, in controller canonical form realization, we have one set of shift register for input. Now, how many inputs do we have here? K is 2. So, we will have 2 sets of shift registers for this, one for this and second set of shift register for this. Now, what should be the maximum memory for each of these shift register? You can see here the maximum power of D is 2. So, we should have 2 memory elements for the first input. Similarly, for the second input also we should have 2 memory elements. Let us call it U0 and U1. Now, there are 3 outputs. So, the outputs are, this is one output, D times the first and 1 times U1. So, D times the first input is this and 1 times second input. So, that is this. So, this is your first coded bit. Let us call it V0. Now, what is the second coded bit? This is this term. D square U0 is this term and D square U1 is this term. So, this is your V1, and the third output is this. So, this is just a minute, U1 and 1 D term and D square term. So, this is your controller canonical form realization for this generator matrix. So, this is precisely what we have here. We can see. So, this shift register is for this input and this shift register is for this input. Maximum memory element for the first one is 2, second one also 2, and we can see now the first output is D times U1, which is this, plus u2 times this. The second output is d square times u1 and d square times u2. So, that is this, and the third output is u1, which is this, and this is u1 d times u1 d square times u1. So, that is your third output. Okay. Now, this was a non-systematic encoder. Can we find an equivalent systematic encoder or systematic encoding matrix for this generator matrix? The answer is yes. So, how do we find a systematic encoding matrix? So, this has to be put in the form like this 1 0 0 1 and some matrix here. Let us call it A1D times A2D and B1D times B2D. So, we will have to bring this matrix in this particular form. So, we have to get this to 1, this to, this has to be changed to 1, this has to be brought to 0, this we have to brought to 1, and this we have to bring to 0. Now, we will do elementary row operation to get an identity matrix here. So, let us do that. So, first thing that we do is we make this a 1. How do we make this a 1? We do this transformation that row 1 is row 1 by d. So, we divide this whole thing by d, what we get is 1 d 1 by d. Next, we would like to get a 0 here. Here we would like to get a 0. How can we get a 0 here? So, we will do this transformation, row 2 is row 1 plus row 2. If we do that, so we add these two, this will become 0, this will become d plus d square, and what we will get is this. Next, we would like to get a 1 here, How can we get a 1 here? We divide row 2 by this. So, we do this transformation that row 2 is row 2 divided by d plus d square, and once we do that, we get this. Next, we would like to get a 0 here, right. How do we get a 0 here? We multiply row 2 by d and add it to row 1. So, we do this transformation that row 1 is row 1 plus d times row 2, and when we do that, we get this. So, this is our equivalent systematic encoder for the generator matrix, this. Okay. Next, is this equivalent systematic generator matrix, is it realizable? If it is not, find out an equivalent realizable generator matrix and draw its corresponding minimal encoder realization. Now, note here, this generator matrix has a term 1 plus d square in the denominator. Now, this cannot be realizable. So, any denominator term that we have, it has to be of the form 1 plus some polynomial here, but here this 1 is not here. So, we cannot realize a rational function of this form using our shift register. So, this particular equivalent systematic encoder is not realizable. However, if we multiply this by d square, what we get, if we do this transformation, what we get is this. This is no longer, so what we are getting now is basically a new equivalent encoder, which is in the feed forward form, and it is realizable. So, how do we realize it? Again, if we are using controller canonical form realization, we will have one set of shift register for this input, another set of shift register for this input. What is the maximum memory for the first row? The maximum power of D is 1. So, we will have one memory element for the first input. And what is the maximum power of D for the second? That is 2 here, 2 here, 2 here. So, we will use 2 memory element for the second input. And again, what are our outputs? There are 3 outputs. The first output is this. This is U1 times this, just U1. So, this is this. Second one is D square of U2. So, D square of U2 is just this term. So, this is my second output, and the third output is this D times U1D, which is this one, and 1 times U2D and D square times U2D. So, that is this. This is our third output. Now, given below is a rate 2/3 systematic convolutional encoder. Please note, this is neither in the controller canonical form realization or in the observer canonical form realization. Note here, the feedback terms that are coming here are not only coming from the same encoders like this. Feedback is not only, so if you look at the feedback, feedback from this is going to this encoder, and feedback from here is going to this encoder. So, not only feedback is coming to the same encoder, but it is also going to the other encoder. So, this realization is a very compact realization. The question that is being asked is, can you find out the generator matrix corresponding to this encoder? So, how do we find the generator matrix? We know this is a relation between the input and the output. So, how these inputs are getting mapped to the output, that is governed by this generator matrix. So, what we are going to do is, we are going to write the output V d in terms of input U d, and then that would give us our generator matrix. So, our objective is to write V1, V2, V3 in terms of U1 and U2. Fine. We use some auxiliary variables x and y, which basically will help us find the contents here. So, if this is x of d, this term will be d times x of d, and this will be d squared times x of d. Similarly, if this is y, this term will be d times y of d. So, what is V1 of d? V1 of d is U1 of d. You can see U directly goes, this input directly goes here. So, V1 of d is U1 of d. Similarly, this input UD directly goes to the output here. So, V2 of d is U2 of d. Now, what is V3 of d? V3 of d is this term, which is x of d, this term d times x of d, and this term which is d square x of d. So, it is this term plus this term. So, it is these 3 terms. Now, what is this term? This is y of d. So, we have written V1 of d, V2 of d, V3 of d in terms of U1, U2, x of d and y of d. Now, note, we need to get rid of x of d and y of d, and we have to write these in terms of U1 and U2. Now, what is x of d? X of d is this and this. Similarly, what is y of d? Y of d is this term, this term, sorry, this term and this term. Okay. So, we can write two more equations for x of d and y of d. So, again y of d, as I said, is u1 of d, y of d is u1 of d, which is this one, this is u1 of d plus d square x of d. D square x of d is this term, d square is x of d is this term, which is coming here, this term, and this another term here, which is d times y of d. So, d times y of d, note here the third input here is this one, which is d times y of d. Similarly, x of d is, first one is this term, which is u of d. So, this is u of d, and the second term is this term, which is d times y of d, this one. Okay. So, now we have got equations of y of d of x of d in terms of u1d and u2d. So, let us write, bring y of d at one side and x of d at one side and write them in terms of y of d and x of d in terms of u1d and u2d. So, if we solve this, what we get is y of d is given by this and x of d is given by this. Now, we plug these values of y of d and x of d given by this into here, into this expression of y3 of d. So, we plug this value of x d and y d, which we just computed, we plug those values in here. If we do that, we will get the expression of y3 of d. Okay. Now, so if we do that, finally this is v3 of d. Okay. So, if we do that, what we get is then v3 of d is this times u1d plus this time u2 of d. So, now we are in a position to write the generator matrix. The first equation that we will require is this one, second equation we will require is this one, and the third equation that we will require is this one, right. So, you can think of it as like this. So, we have 3 output v1, v2, v3, 2 input u1, u2. So, we are writing v1d, v2d, v3d in terms of u1d, u2d and this G matrix. So, what is v1d? v1d is u1 of d. So, then our G matrix here, again this G matrix is 2 cross 3. So, v1d is u1 of d. So, we get 1 0. v2 of d is u2d. So, we get 0 1. And what is v3 of d? v3 of d is this times u1 of d and this time u2 of d. So, this will be our final generator matrix corresponding to the encoder that is shown in this figure. Okay. Now, the next question is, can we realize this encoder in the controller canonical form? So, the answer is yes, we can realize it. We already have the expression for generator matrix. So, to realize it in controller canonical form again, so there is one set of shift register for each input. So, this is one input, this is second input, right. Please note this is a feedback polynomial. So, we would require a feedback polynomial, and now maximum degree here is 3 and maximum degree here is also 3. So, we will require two set of shift register. First one is this one, Please note this has 3 memory elements, and similarly second shift register, this also has 3 memory elements. That is because the maximum degree of this rational function is 3, and similarly maximum degree of this rational function is 3. And we just implement this. So, V1d is just U1d, so that is this. V2d is U2d, that is just this. Now, what is V3d? V3d is 1 plus d square plus d cube divided by 1 plus d plus d3 U1d plus 1 plus d square plus d cube 1 plus d cube U2d, right. So, relationship between V3 and U1d is given by this. So, let us implement this. So, numerator has 1 plus d square plus d cube. So, you can see here this is my 1, this is my d, this is my d square, and this is my d cube. And similarly the denominator has 1 plus d cube. So, the denominator, this is the 1 term, this is the d term, and this is the d cube term. So, this part is implemented. Next is this. Following the same procedure, we can find out the mapping between U2d and V3d. The feed forward connections are 1, d square and d cube. So, then this is 1, this is d, no connection, d square is this, and d cube is this. Similarly, the feedback connections are 1, d and d cube. So, feedback connections, this is the 1, this is d, and this is d cube, and V3 is a combination of these two. So, this is my V3. So, I hope this is clear how we can realize this encoder using controller canonical form realization. Now, the next question is how many termination bits are required to bring this encoder back to all 0 state. Now, what does termination means? Termination means we are bringing this encoder back to all 0 state. So, no matter what the state is, if we want to bring them back into an all 0 state, the number of termination bits required is equal to how many memory elements we have. So, in the controller canonical form realization, to bring this shift register, the first shift register, if you want to bring it to all 0 state, we would require 3 bits, because we have 3 memory elements here, 1, 2 and 3. Similarly, for this shift register we require additional 3 bits. So, 4, 5, 6. So, total we require 6 termination bits, 3 to terminate this encoder and 3 to terminate this encoder. So, we require 6 termination bits. Finally, let us come to the BCGR algorithm that we talked about. So, the first question is, can you write the a priori probability in this particular form, and also the branch metric in log domain, can it be written in this particular form? Now, UL is my input, LA is the APP value for the a priori inputs, LC is the reliability factor which is given by 4 times ES by N naught. Other notations are same as which are used in the lecture. V is code word, R is a received sequence. So, can we write these in terms like this? So, let us look at it. So, what is the probability of u being +1 or -1? let's take like plus 1. Let's say what's the probability UL is plus 1. Now this can be written as this by 1. So I can write as probability of UL being plus 1 times divided by probability UL is plus 1 plus probability UL is minus 1. I write it this way, right? And if I divide by probability of UL being minus 1, then what I get is probability of UL being plus 1 by probability of UL being minus 1, 1 plus probability of UL being plus 1, probability of UL minus 1. So this is what I will get of the form here. You can see here the form for when UL is plus 1, I get probability of UL being plus 1, I get in this particular form. Now let us look at what is the probability that UL is minus 1. Again I can follow the same procedure. I can write this as same as this by 1, or I can write a probability of UL is equal to minus 1 divided by probability of UL being plus 1 plus probability of UL being minus 1, and I can divide this by probability of UL being 1. So this will be probability of UL equal to minus 1 by probability of UL being plus 1, 1 plus probability of UL being minus 1, probability of UL being plus 1, right. Now this I can also write as this is equal to probability of UL being plus 1 by probability of UL being minus 1 raised to power minus 1, and this is 1 plus the same thing raised to power minus 1. So if I combine this and this, what I get is the first step here. Okay, I can write by combining this and this, I will get this. Now if I write this ratio of probabilities in terms of L values, so what is this L value of UL? This is log of probability of UL being plus 1 by probability of UL being minus 1. So this can be then written as e raised to power LA UL. So if I do that, if I plug this in the first line, what I get here is this term. Okay. Now note, I can further simplify this into this expression. You can see when UL is plus 1, when UL is plus 1, what do we get? When UL is plus 1, this is e raised to power LA UL by 2 and e raised to power minus LA by 2. So this will be basically 1. So this will be 1 times 1 plus e raised to power minus LAU, which can be written as e LAU 1 plus e LAU. This is precisely what I have written here. And if UL is minus 1, this will be e raised to power minus LAU by 2 and e raised to minus LA by 2. So this term will become, in that case, e raised to minus LAU 1 plus e minus LAUL. So this term can be written in terms of this, right. And what is this term? What is this term? This, I can simplify this term. Let us make some space. I can simplify this term as e raised to power minus LAUL by 2, and I have e raised to power minus LAUL by 2. This is e raised to power LAUL u l by 2 plus e raised to power minus L A u l by 2. So, what I am doing here is I am writing this particular term. So, this I can write as this and this. So, this cancel out and this is e raised to power x plus e raised to power minus x. This will be cosh of x and that is a symmetric function. So, it does not depend on sign of u l, whether u l is plus 1 or minus 1 does not depend on that. So, I can then write this in terms of this expression. So, we will use the expression that we derived in the previous slide for a priori value, which was u l being plus 1 or minus 1 as a l e raised to power u l L A u l by 2. We will use this expression to simplify the expression for branch matrix for our BCJR algorithm. Now, note, if you recall, we have written the expression for branch matrix as a priori probability u l, and then we had for AWGN channel we had this expression, and of course, there was some constant factor which did not depend on u of l, right. So, what we did just now was we derived that this a priori probability can be written in this particular fashion, right. Now, let us further simplify the expression for branch matrix. So, this we can expand as r square plus v l square plus 2 times dot product of r and v l. Now, this does not depend on choice of v of l, and if v of l is mapped to plus 1 and minus 1, v l square will be 1. So, this also will be a constant term. So, this term would then not depend on choice of v of l. So, what then we will be left with is, so this term we can just take out as some sort of constant which does not depend on choice of v of l, and what will be left is this term which we are writing here, and the next term that will be left is this term which we are writing here. Please note, LC is 4 times ES by N naught. So, that is why we are writing it as e raised to power LC by 2 and dot product between R and VL. So, then we can just simplify this expression as some constant terms multiplied by this a priori term, and this is a term which depends on received channel values. So, this is a simplified expression for branch matrix computation for our BCJR algorithm if we are considering additive wide Gaussian noise channel. Now, if we consider branch matrix in the log domain, then log of this term will be some sort of constant, we just ignore it because this does not depend on choice of v of l, u of l. So, then this will become u l, l value, a priori l value by 2 plus L C by 2 and dot product between the received sequence and the transmitted code word. So, this will be then our simplified expression for branch matrix computation for BCJR algorithm over additive wide Gaussian noise channel. Thank you.